Good morning, good afternoon, everyone. I'm sorry we are a bit late today. There was a few technical issues, but now everything is solved. Thanks very much, Funelma, for helping us. She's in the background. You don't see her. She's doing all the technicalities. So thank you very much for helping us. So welcome to the new event of the ESO Hypatia Colloquium series. We are very glad to have today two young early career speakers. In this case we have Oliver Herbort and Sophie Beaumont, and I hope I made the pronunciation properly, and I apologize if I didn't. So as you well know now, basically this is a series especially devoted for early career scientists, and we are very glad to have this chance to have all these beautiful talks. And we are running to the end, but we will certainly repeat these next year. But for the moment, we are very grateful to the speakers and very grateful to the people attending the event. There's always a lot of people, and a lot of people are also watching the event later on YouTube. Please be reminded that the video, in fact, is available online and on our dedicated channel, so they can always be seen. As well, please be reminded that if you go to the Hypatia Colloquium pages, you will see the program, and together with the program, you can click on the title of the talks of each speaker, and then you can download the CVs of the speakers so you can meet them better and know about them and about their excellent science that they do in the career. Finally, if you want to, I remind you to the people, if you want to make a question after, so now there will be two 30-minute slots, 30 minutes for the first speaker and 30 minutes for the second speaker. The talks are more or less 20 minutes plus questions. If you have questions, please make your question. If you are in the Zoom meeting, you can make it directly your question. Just raise your hand and I will give you the word. From people on YouTube, you can type your question on the live chat, and then we will pass the question to the speakers. With this, we can start with Oliver. So Oliver, you are there, right? So Oliver is yes, welcome, Oliver. Oliver is a PhD student at the St. Andrews University in Scotland. He did a master thesis in physics at Göttingen in Germany. He will defend the PhD next year, so good luck. The final year. Oliver has a very interesting science expertise. His research focuses on combining astrophysics and geological knowledge in order to understand the interaction of atmosphere and surface of rocky planets. So this is absolutely fascinating, and we are really looking forward to see your talk. So please go ahead. Do you want me to give you the 5 minutes, or you like to go on and then I can?
I have the time on my screen share. It should be fine.
Good. So please go ahead. Thank you.
So yes, I'm Oliver Herbort, and I'm going to talk to you about the atmospheres of rocky exoplanets, especially how we can get from their clouds to their crust. So not everyone in the audience will be familiar with exoplanets on a day-to-day basis. So just a brief introduction to what I mean with rocky exoplanets. And the first plot I'm showing here is actually a selection of planets that we do know, where we actually have a measurement for the mass and the radius. The planetary mass on the x-axis, planetary radius on the y-axis. We have this large blob of planets which are quite large, which are these Jupiter-esque planets, some really hot, some colder. But with respect to rocky exoplanets, we don't really care about those. We care about this bottom left corner. The bottom left corner defined by less than 8 Earth masses, less than 2 Earth radii. That's where rocky exoplanets live. Some of them may have a relatively large gas envelope still, but that's roughly the area where we actually want to investigate things. And that is where these planets actually have a crust, which is somewhat rock-like. So what we can do is measuring the planetary mass and the planetary radius, like it's indicated in this kind of graph here. But what we actually really want to know is, how does the surface look like? Is the planet some planet without an atmosphere at all, some Mercury-like planet? Or is it something with a thick atmosphere, 100 bar atmosphere, Venus-like? or is it something like Enceladus or Europa, like covered in basically in ice? Or is it something like our own Earth, which is partially liquid water, partially land surface as rocks? So that would be the ultimate goal, how to differentiate between all of these different kinds of atmospheres. And especially we want to focus on whether something is bone dry, where there's no water at all on the surface, or there's actual water on the surface, and one might have some exposed lands, and that would then be wonderful to actually consider for the formation of life on such a planet. But the actual gathering of information is quite limited. There are limited possibilities for that. And one technique is the transmission spectroscopy. So when the planet actually travels in front of the star and some light travels through the atmosphere, indicated by the upper two red light rays up here. But actually it's traveling not through the atmosphere directly above the crust, it's traveling through the relatively high atmosphere. And if there are some certain molecules in that high part of the atmosphere, one can get absorption features in there and therefore get to know the molecular abundance or the molecular composition of the high atmosphere. If there are some clouds in that region, one can get some scattering effects or so, or some fingerprints of some molecules, so that we can actually get the molecular composition or the condensate composition of those clouds. However, what we actually do want to know is how the crust is looking like, how is the low atmosphere looking like. In order to understand that, there's just so much more going on, and I just want to mention a few things. First, when we're starting from the crust-atmosphere interaction, there is in and out gassing from the planet itself. There can be volcanism providing new gas to the atmosphere. There can be tectonics, so basically some rock being drawn down to the mantle of the planet. Chemical weathering can actually is the effect of actual some atmospheres changing the rock, chemically changing the rock. If there is biology in that planet or on that planet, there will be some additional biological fluxes. So that can have a huge effect on the atmospheric composition as well. If you go higher up in the atmosphere, as I mentioned, clouds, they can actually do change the element abundances below the cloud layer and above the cloud layer. All those elements that actually condense in form of some condensates will be depleted higher up in the atmosphere with respect to below the clouds. If we go even higher up, atmospheric loss, parts of the gas of the atmosphere can be lost to space, especially the very light elements like hydrogen or helium. Last but definitely not least, there's photochemistry altering parts of the atmosphere via stellar radiation coming, or also cosmic rays, and that's a whole other can of complexity. But for the moment, we just want to focus on the crust-atmosphere interaction. So the very bottom part, and calculate it so that we can get some insights to what the surface conditions are like, and to set preconditions for the cloud formation, which is actually the second part of my talk. So what kind of model are we using? The model is an equilibrium condensation model called GGChem by my supervisor, Peter Voigtke, from a paper from 2018. And it basically takes an input of multiple different elements, actually going up to iron. So we take a certain amount of hydrogen, certain amount of carbon, nitrogen, oxygen, but also potassium, calcium, titanium, and so on. In a given ratio, that's one of our input parameters, the ratio of these elements, so-called total element abundance, put them into a cauldron under a given pressure, given temperature, indicate here with the pressure at the temperature, and then calculate what's most stable in the gas phase. So the gas phase is then calculated by minimization of Gibbs free energy. However, if you just minimize the Gibbs free energy for the gas phase, there will be some supersaturated molecules, but we also form condensates, which then remove parts of these supersaturated molecules in order to not have anything supersaturated. So we are in chemical equilibrium and also phase equilibrium with the crust, so that we can have for one input parameter of the element abundance an estimate of the crust composition and the gas in the near atmospheric crust. So I want to talk a bit about the total element abundances as an input. And therefore, I have this plot here, which shows on the y-axis elements with respect to silica, and on the x-axis different elements. And I really want to focus on two of these: the bulk silicate Earth as the diamonds, which is our Earth except for the core, and then just counted whatever is in there, and the CI chondrite, which is a leftover rock from the formation of the solar system, which is formed quite far out in the solar system, which is pretty rich in volatiles, so atmospheric loving species. We can see this by the increase here in abundance in hydrogen, carbon, nitrogen, but also in phosphorus or sulfur. However, something like magnesium or aluminum are basically similar, basically equally abundant for both of these. So that will result in different atmospheric compositions. But now let's take a look in what these atmospheric compositions actually look like. The first of a few busy plots, but don't worry, I'll walk you through it. We have here on the x-axis the temperature range from 100 to 5,000 Kelvin, and the molecular abundance on the y-axis. The input is a bulk silicate Earth, and the pressure is set to 100 bar for all of these different temperatures. For the very high temperatures above 3,000 Kelvin, almost all of the rock is vaporized. So we have actually a metal oxide rich atmosphere. That's like all of these lines are basically metal oxides. Then above 2,200 Kelvin, oxygen is dominating. Oxygen, the most abundant species in rocks itself, in silicate rocks at least. So that is just because you vaporize the rock. If we go lower down in temperature, the most abundant species are water, sulfur dioxide, and carbon dioxide, with different temperatures where they actually kind of get incorporated in the surface composition, and then leaving nitrogen at the end. If we compare this to the CI chondrite, we get a very similar view. We have the metal oxides at the high temperature end, water dominating a wide range of the temperature, even a wider range than the bulk silicate Earth, just because there's so much more hydrogen in the model, and then carbon dioxide. But also we have the coexistence of carbon dioxide, methane, and water in a certain temperature range, and then also hydrogen and carbon monoxide. But when we compare these two, we see a difference in where the hydrogen actually goes into the crust. And the question is, where does the hydrogen actually go? For the bulk silicate Earth, the gaseous water does not translate into liquid water or solid or water ice at least even, but rather into these two species here. This is now the temperature range of 100 to 1,000 Kelvin. So these two species called soda phlogopite and phlogopite, which are phyllosilicates. What the heck are phyllosilicates? Phyllosilicates are hydrated rocks. So there's basically, you have silicate and you just stuck some OH into parts of their lattice structure. So they just eat up water and basically get hydrated. If we compare this to the CI chondrite model, we see that there's a huge variety of these phyllosilicates. All of these solid lines are different phyllosilicates that are present in the crust composition. And then on top of that, there's actually most of the water or most of the hydrogen incorporated in liquid water, and for lower temperatures, even water ice. So the question is, can we actually force our bulk silicate Earth model to also form liquid water? And that's by increasing hydrogen and oxygen abundances. We can actually saturate the phyllosilicates here. In this case, for 12% mass percent of additional water, we saturate a certain range of temperatures with hydrogen so that there's liquid water stable. But for below, the phyllosilicates are not yet fully saturated, have not fully formed, so there's no liquid water or no water ice. So we have to add even more water. We can do so, and we have them fully saturated, and we can get liquid water. So far, I've only talked about the near crust atmosphere in contact with the crust itself, but an atmosphere is more. And therefore, I want to introduce you to our bottom to top atmospheric model, where we actually start with our atmospheric crust interaction, as I've just talked to you about before. And then we build our atmosphere from there on higher up into the atmosphere. We assume a hydrostatic polytropic atmosphere, which then has a pressure temperature profile as it looks like in this plot here on the left-hand side. So just decreasing with it with height in temperature. And what do we do in each atmospheric layer is that we actually solve chemical phase equilibrium. And every time when some new condensate becomes stable, we remove all of the stable condensate from the model and only take the gas phase to go into the layer above. So we basically deplete the atmosphere with regard to everything what becomes thermally stable. This is no kinetic cloud formation. That's just another step. But as that is very time-consuming and computationally time-consuming, this is a really fast and simple approach to basically give a first-order insight to what clouds could form on different rocky exoplanets. If we take a look at the CI chondrite for 1 bar surface pressure and 350 Kelvin surface temperature, for the gas phase, the right-hand side here is the bottom of the atmosphere, and we go to the top of the atmosphere to the left, where we have the molecular abundances again on the y-axis. We start our atmosphere with methane, the black dashed dotted line, water, the blue line, nitrogen, the gray line, and also some carbon dioxide, but also methane. And we see also that there's a significant decrease throughout the atmosphere in water, in hydrogen and carbon dioxide, but also in HCl and H2S. And this is caused by the condensation. The question is, what condensates do we get? And this question is answered with this plot, where we do have the condensates that actually are removed. So the blue, water. So water is thermally stable throughout the entirety of the atmosphere. We remove it in every atmospheric layer. We will remove a bit of water. In the low part of the atmosphere, graphite is actually removed from the atmosphere. So it's pure carbon condensed as graphite. And then 2 ammonia species, ammonium chloride and ammonium hydrosulfate. Ammonium hydrosulfate, for example, is also quite interesting because that is also one of the cloud layers proposed for Jupiter. So as we're not just interested in one pressure and temperature point, we want to basically sweep across a wider range of surface temperatures. That's why I introduced this kind of plot, where we have surface temperature of 300 to 1000 Kelvin and the atmosphere now on the y-axis. Each model, let's say for a 400 Kelvin surface temperature, will just be this one column reaching 300 Kelvin at this dotted line, 200 Kelvin here at 10 to the minus 1.5 bar, and then ending at roughly 160 Kelvin. If we add our cloud condensates that we do have, the first thing that we notice is that we have a gap in between of these. So we have a few clouds, different cloud species at the bottom of the atmosphere, or not at the bottom, at the high temperature part of the atmosphere, and quite a lot of different cloud species at the top part of the atmosphere. Talking about the high temperature ones first, there's sodium chloride and potassium chloride, the 2 bluish ones, and iron sulfur, FeS, as the high temperature condensates. Whereas for the colder temperature range, the 2 blue colors are water, liquid water being the darker blue. There's graphite, this black outline here, but also, as we mentioned earlier, ammonium chloride at roughly 300 Kelvin, and then ammonium hydrosulfate at 150 Kelvin, as well as S2 clouds around 200 Kelvin here. If we compare this to the BSE model, the bulk silicate Earth model, we see a very similar view. We still see this high temperature condensates quite separated from the low temperature condensate, but there is graphite, which is actually the only condensate that we find that can breach this gap of the high and low temperature condensates. So graphite is something special, and I will mention something more on the next slide about that. But another thing that I want to mention at this point about this slide is that we have water. If you remember from earlier, the bulk silicate Earth model has definitely no water at the surface. There's no liquid water stable at the surface. However, we still do get water clouds high up in the atmosphere. So talking about the graphite, which is here in this quite narrow region of roughly 500 to 650 Kelvin thermally stable. So that is actually a result from the gas phase. And therefore, I just want to introduce you one further type of plots, which is actually from a paper from earlier from this year, where we have on the x-axis the carbon content relative to hydrogen, oxygen, and carbon, and oxygen to hydrogen ratio on the y-axis, which means that at the very top, we have a pure oxygen atmosphere, and the bottom, we have a pure hydrogen atmosphere. Nitrogen is also included in these calculations, but it's basically only forms N2 everywhere. So one can put that aside. If we look at planets in our solar system, we have Jupiter in the bottom left corner, an H2 atmosphere, Titan, methane atmosphere, Mars, Venus, top right in a CO2 atmosphere, and Earth, when we don't consider the nitrogen, we have almost a pure O2 atmosphere. But actually, the interesting part here is that we actually have three different regimes. One inside of this triangle, which is type C atmosphere, which has the coexistence of water, carbon dioxide, and methane. And then the type B atmosphere above the triangle, where we do not have any methane anymore, but rather have O2. And in the type A atmosphere, where instead of the carbon dioxide, we have H2 as a thermally stable, not a thermally stable condensate, but as a molecule that's in the gas phase. This is pretty robust against temperatures, this kind of diagram. And even if we include more molecules, more elements, this actually is really, really robust. If we do so, if we actually take a look at all of the different atmospheric models, so each line here, each colored line is one specific model from the previous atmospheric models that I've talked about. And we see that they evolve kind of. They start, for example, 600 Kelvin model starts at this point, travels a bit in this diagram, but it stays in this triangle. It stays as a type C atmosphere. And the only models that go outside of this type C atmosphere are the ones of less than 510 Kelvin. And they actually fall into type A atmosphere. And they do not have graphite condensation anymore, because graphite condensation is only possible as a type C atmosphere. But what we see, what is interesting to see, is that we actually do not have a change in atmospheric type for any atmosphere by condensation of clouds. There can be a change in atmospheric types by changing the surface conditions, though. For the CI chondrite, we all stay inside of this triangle as a type C atmosphere. If we want to go back to water clouds and just take a look at the water clouds, and as I said, we do have water clouds for the bulk silicate Earth model as well. And as we did earlier, let's saturate the crust composition and let's put more hydrogen and oxygen in there. What happens is that we can drag down the water cloud base quite significantly. This is now 8%, so definitely no water at the surface yet, but we already dragged it down quite a lot. If we drag it down so far that we almost get liquid water stable, for higher pressures we would, but not for 1 bar atmospheres. It's still not there yet, but there is it's pretty close to the crust. So finding clouds close to the crust does not necessarily mean that there's water already at the surface stable. But if we saturate it fully, we can get liquid water stable at the surface. And then we also have a stable water ocean, basically. The last thing that I want to show is to vary the surface pressure and surface temperature, because so far we kept the surface pressure at the exact same. But at this plot here, we change the surface conditions along this black line here, which allows us to have the exact same pressure and temperature profile in the higher atmosphere. So all of these pressure temperature profiles go through 300 Kelvin at 1 bar. And we see that independent of surface temperatures, we have a range where we actually do have liquid water as a stable condensate. So this would be really interesting to further investigate in order to think about aerial biospheres, so potential life in an atmosphere, because there is liquid water, and in some regions there might be also some nutrients available. So that's a really interesting result from this already, that we can get water clouds, liquid water clouds at high surface pressures as well. But if we include now further condensates, further cloud condensates, we have roughly the same regime again. We have the high temperature clouds, the low temperature clouds, but there's one additional condensate that I want to mention here, H2S, which is only stable above surface conditions where we actually do have a relatively high surface pressure. So if one would hypothesize to find H2S as a condensate in some of these exoplanets, one could have an indicator for having high surface pressure, at least based on this simple equilibrium chemistry model. So with this, I would like to thank you for your attention and leave you with my take-home messages. And if anybody has any questions, I'm more than happy to discuss them. Thank you very much.
Great, thank you, Oliver. Thank you very much for the talk. So we can now indeed open the floor for questions. We have a few minutes to go over questions. So let's see. Again, people on Zoom can raise the hand or put the question on the chat. So while we are waiting, I do have myself some question actually. I apologize since the beginning, Oliver, because it's now my field. Okay, but I was really, so the first question I had, so at the beginning you talked about the element abundances near the, so first of all, thank you very much for really clearly telling us about the difference in atmosphere, how you stratify the atmosphere, study the atmosphere at different heights, basically. And you were talking about the near crust composition and the interaction between the atmosphere and the surface of the planet. My curiosity here is that, so the abundance, in particular, the element abundances that you were describing. So I understand this is fully theoretical at the moment. So but I wanted to, my question as an observer, so which is the observational test bench to which you compare your model? So
as you mentioned, the element abundances are a big unknown.
Yes.
We don't really know what the element abundances overall on a given exoplanet is. There's no way to actually detect that directly. There are a few measurements where some planets have been fallen into a white dwarf. So polluted white dwarfs have been measured. There have been some element abundances deducted from that, and then we have investigated also kind of those atmospheres as like our input to the rock atmosphere interaction. The idea basically is to take to basically have the initial element abundances that are available for a planet, and then calculate what happens to this planet when we just let it rest for a long time. And then we have this element abundance available at the surface, and then this will be in the gas phase, this will be in the rock phase, and the rock phase will be like this, composed of that kind of stuff. The observational unknown is, well, is a good question. But if we only look at various different stars in our surrounding, that's actually the Hypatia catalog, which is quite conveniently named for this talk today, where you see how much the element abundances in the stars itself vary. Okay. And that will translate to the rocks or to the element abundances of the planets. So there is a large area where one can play and change the element abundance, because it's really tough to say what the actual planet will be like. And therefore, one has to investigate many of them to then say, when we find something, when we find these, for example, H2S clouds, as I mentioned, to use them to determine the surface conditions, to say, oh, we have these kind of clouds at this pressure temperature. Well, the surface might look roughly like this. And that's what we want to reach with this approach.
But now I understand, so because people were not there, of course, but before starting the event, we were chatting. And now I understand when you were mentioning to me you're looking forward for future facilities to come online, and I understand very well now. So you really, hopefully, we've had the energy, the power to see this, so to measure this at some point, in the future.
Yeah, I mean, JWST will be fun to have, but it will not provide that much information, or not that detailed information about many rocky exoplanets.
Okay.
So unfortunately, we have to wait another generation,
Okay.
of telescopes, and hopefully that doesn't take as long as JWST.
Yeah, let's see. Okay, thanks. So let's see if we have another final questions from someone in the attendees. If not, I have a very last question maybe for Oliver, myself. Yes, I can. So I see no one, so I can make my question. So, no, we have Dietrich. Please, Dietrich.
It was a very impressive, very exciting talk. Thank you very much. Have your models, or would you try to calibrate your models against observations of moons in the solar system? Some of the massive moons in the solar system have traces of an atmosphere.
Yes. Well, thank you first of all for the question. So there are for some of the moons, for Titan, for example, where we have a methane-rich atmosphere. If we just set the correct element abundances for the surface, we can predict some methane-rich atmospheres, which is basically what we see on Titan. So yes, we can provide some tests regarding to these other planets, but they will really have to be tweaked in order to get the correct element abundance. And as there are so many things that are just not included in the model, as we don't have any irradiation, for example, we basically want to use this as a startup for further in-depth models to then provide insights to actual cloud formation. That's the way we really want to go. So it's a very quick and fast model and simple model to get the first order insight.
Okay, thank you.
Okay, thank you, Dietrich, for the question, and thank you, Oliver, for answering and for the talk. And we can now move to the second speaker of today, Sophie Beaumont. Sophie, are you there? Yes, hello, welcome. In the meantime, so if you can start sharing your screen in the meantime. So let me say that, so Sophie, she got a master's degree in, so let me start again. So, okay, she got in l'Observatoire of Paris in France, in astronomy, astrophysics, and space engineering. And in fact, she's now doing a PhD in Toulouse, and she's an expert on X-ray instrumentation and astrophysics, and in particular with high-resolution X-ray spectroscopy with Athena X-IFU. And this is exactly the topic of the talk of today, that we are going to listen to this. So Sophie, thank you very much, and you can start sharing anytime.
You should see the screen.
We don't yet.
Sorry, okay.
No, it's coming.
Okay.
Yes, now it's there. So thank you very much again. Nice to have you with us, and please go ahead.
Thank you. So hi everybody, and thank you for attending this talk. So today I'm going to talk about the Athena X-IFU from detector development to scientific feasibility studies via simulations. And so I would like to start with a bit of context on that first. So about half of the baryons in the universe are in gas at temperature above 10 to the 6 Kelvin. Those can be found in many objects, such like supernova remnants, galaxies, clusters of galaxies, etc. And those are key to understanding the processes governing large-scale structures, such as their assembly, their evolution, whether it's chemical or dynamic. Also, we have about 15% of the energy output in the universe, which is in X-rays. And so we have many of those sources from this energy universe, which includes supernova remnants or supermassive black holes, for instance. And those are key to understanding how the black holes grow and shape the universe. And so the thing about those hot and energetic sources, which are, as we just saw, major props for the understanding of our universe, is that they emit in X-ray domain. And the mechanism by which they emit can be variable. Several emission processes come from the fact that those media are highly ionized, creating the conditions for different forms of photon-electron interactions, such as, for instance, thermal bremsstrahlung or synchrotron radiation, which give the continuum part of the spectrum. But also there are many electrons which are not free, of course, but orbit around the nucleus. And from where we get sharp emission lines superimposed on the underlying spectrum, continuum emission. And so in order to properly study all those sources, astrophysical sources that I mentioned, we need to fulfill several criteria. And for instance, where we want to be able to do high resolution spectroscopy for broad energy range and even for extended sources. And that's the main point. So this means we don't really want to use specific spectrometers or CCDs, whereas microcalorimeters are ideal for those kind of measurements. And on the picture below, you can actually see a great illustration of this, where we have in red the spectra from SUSEP data, which was acquired with CCD, and in black spectrum from Hitomi, so where you have a macrocalorimeter acquiring the data, and you can clearly see the great improvement in energy resolution in that example. So that leads me to the Athena observatory, which is an X-ray observatory from ESA, aiming at implementing the science theme of the hot and energetic universe and answer questions such as, for instance, how does the ordinary matter assemble into the large-scale structures that we see today. So the satellite is scheduled for launch in 2034. And it will be in L1 orbit. And so it will have two instruments, one of them being the X-IFU, X-ray integral field unit, which is the one I'm particularly interested in for my PhD work. So the X-IFU is a cryogenic imaging spectrometer based on TS microcalorimeter array, which will have a bit over 3,000 pixels. And so some of the key parameters for this instrument is that it will look at X-rays from the soft band energy range, so 0.2 to 12 keV, and will have the impressive energy resolution of 2.5 eV up to 7 keV. So to give you an idea, a feeling that's like after 50 times better than current CCDs. So that will be great. And so now that I've given a bit of context for this talk, before going further, I would just like to point that I will talk about two very specific aspects of the development of the X-IFU instrument, which are the ones so I'm working on. So there's the TS detectors development, and then I'll go over a science case study. So first, if we start at the heart of the X-IFU, well, we have the TS detectors. So you can see on the picture here, like a nice prototype of the wafer with its like characteristic hexagonal shape. So it's actually not that big. The wafer itself is like 9 centimeters tall. And at the center, we have the array of detectors, which is like 2 square centimeter area. And if we take further zoom in now to see how those detectors look like in a bit more detail, that's what we get. So if look, for instance, at the picture at the bottom left, at the top of the detector, we normally have an absorber, which actually is not shown at this bottom picture, but which basically absorbs the X-ray. And underneath the absorbers, we have the TS detector itself with some stems, which hold the absorbers. So those are the blue dots that you see, and then the leads, so the bias leads. And all this rests on a layer of silicon nitride, which is itself on the silicon wafer. And you have just above this like a 3D view of how that would look like, where you can actually see the absorbers, which are the big squares, and one of them you can like remove to show the TS underneath that. But so how does those TS detectors actually work? So basically, they are thermal detectors, and they measure the tiny amount of heat that X-rays deposit when they hit the absorbers. So you can have different types of microparameters, but this specific one, the TES, transition edge sensor, are made with the thermistor in superconducting metal. And the reason why we want to use this superconducting metal is because then we have resistance versus temperature, which looks like the plot you have here at the center. So above a certain temperature, which is TC, or critical temperature, we have the metal is just normal, which means it just behaves like a normal metal. And below that temperature, then it becomes superconducting. But what is very interesting is the transition in between, which is very, very sharp. And as you can see on this plot, if you imagine a very small change in temperature when you're in this transition, then you have a very small, very large, change in resistance, which is what we use to have this great sensitivity for those detectors. And I would also like to point out that for our detectors, the TC is very low. It's like 90 millikelvin. So basically, those are cryogenic detectors, right? We need to operate them at very, very low temperature. So if you don't have any X-rays, well, nothing happens. That's what you see on the current graph that I have on the right, is just like the baseline. But then when X-ray hits the absorber, the energy is, well, absorbed and thermalized by it. And this leads to an increase in temperature, followed by an exponential decay as the heat is conducted away through the heat bath. And so this change in temperature leads, as I said before, to change of resistance. And since the detectors are biased with a constant voltage using the shunt resistance, a change in resistance means a change in current. And so we measure this change in current with the squids, the rest of the readout. And so you can see a typical X-ray pulse now on the plot on the right, where you have this increase and decrease. So I have to say that this is a very simplified plot. The X-ray or the pulse in current is actually not exactly as simple as shown here. The rise time is not instantaneous, but that was to give you an idea of how this works. And so later on, we can recover the energy of the X-ray from this because it's proportional to that pulse height. So those detectors, they've actually been developed for quite some time at NASA Goddard Space Flight Center now, and they've been more recently chosen for the Athena mission. But so the design is close to final, but there is still some fine tuning that's needed that needs to be done specifically for X-IFU. So here I'm just going through a very quick example of one of those design development that we do. You can change, for instance, the aspect ratio of the TS and of the stem geometry. So actually, if I just maybe go back just a few slides right here, by the aspect ratio, I mean, here you can see that the TS, so the orange square, molybdenum in gold, that's almost square in that picture, but you can make it much more rectangular thin if you want to. And you can also, for instance, change the number of stems, so those blue dots that you have here. Like here. And so those, we would like, for instance, to change those in order to reduce one of the specific noise that we have in the detectors, called the excess noise. And try to also adjust the slew rate that we have. And so, for instance, in the recent tests that we've done, we've looked at different geometries where the TS is not squared, but like 60 by 30 micrometers versus 40 by 50 micrometers, and also looking at 2 steps or 6 steps. So this sort of small changes can actually have an impact on the detector that we want to be able to improve the performance. And so that's what you can see on the plots here, basically at the bottom, where you have a lower thermal conductance, the bath with a higher aspect ratio, or a reduced number of stems. And you can also play on the noise like this. So I'm not going to go into more detail here. If you have more questions after, you can let me know. But testing the TS detectors is of course very critical. I mean, in order to fine-tune that design, but there's also a lot of work that's being done in the team at the moment to do this TRL demonstration of technology readiness level, which we need to do, prior to the mission adoption by ESA in 2022, and also for flight. So I'm obviously not going to go through all those different things that we want to check and we need to prove to show that the detectors are ready for flight, but just give a quick status on 2 of them that are highlighted down there that I'm working on myself. So one of the things that we want, of course, is to make sure that the TS detectors can maintain their performance through the whole life of the mission. And so this starts basically when we are still, on Earth, preparing for flight and everything that will need to be done. But if the detectors are not maintained in suitable conditions with higher humidity, or for instance, things like that, this can lead to changes in the properties of the absorbers, and then lead, for instance, to secondary tails in the pulse shape or low energy tail in the histograms or spectra, which are things that we don't want, of course. And so we need to study all this to know exactly when the conditions are good or not, and define the appropriate storage condition for those detectors for all the process for AITA, for instance. So we have concern for different processes that may effects that may happen. Which can be, for instance, oxidation of the absorber or interdiffusion of the gold and the bismuth in the TS itself. So those are the things we are trying to look at here. And I just actually started again those experiments in the lab after coming back from the COVID break. I mean, put it like that. And so now what I started to do was actually looking at the humidity first before looking at the other parameters later on. And I'm just going to show an example of how humidity can impact our detectors. So first, I did some measurements before, when the detectors were straight out from the fabrication lab. And we get this nice spectra on the left here without what I call aging. So just, testing it right away. And we have very good energy resolution of like 1.8 EV for X-rays at 6.4 kV. And so I took this detector chip and placed it for 2 weeks in a dry box with a Petri dish inside, raising the temperature to the humidity, to 55 to 70% humidity, and retesting it afterwards. And now we can see we're taking the same spectra where we have the ice shape here, that now the line shape is distorted. We have this low energy tail just before the line itself. And in order to fit that properly, now we need to add a tail in the feet, like an exponential tail. If we don't do that, we have the energy resolution, so we just deteriorate to 2.1 EV instead of the nice 1.8 EV that we have. And so afterwards, I redid the test once again, putting the chip in even higher humidity for another 2 weeks. And that's now this slide. So we can see that the strength of the tail has increased further. And now it's like we're like 21% strength of this tail. So this test is still ongoing. That's just preliminary results. We need to spend more time looking at all the different parameters, etc., in order to define the proper activation energies and things like that, and define the proper condition to store our detectors. But yeah, that's a start. So I see that time is running. So I was planning to talk about another aspect of the life of the detector. So the first part was this kind of aging when we are on Earth, but then once you send the detectors in orbit, you have other things that may affect their performance, which are the radiations, from the radiation environment. And so that's also something that we are looking into, and which is actually not, it is something fairly new, because there is a lot of work that's been done, in the past in the radiations for CCDs and like semiconductors, but for superconductor detectors, that's something very new. So we need to look at that. But if you have questions, feel free to ask afterwards. But now I think I'll just skip to my last part because, yeah, like I said, time is running. So I've been talking about the development of the instrument, or a very tiny part of this whole development by those tests that I'm doing on the TS detectors. But it's important to remember that all the key parameters are specified from the core science objectives themselves, right? And so one of those core science objectives is to study the bulk, motion, and turbulence in galaxy clusters. And so basically, the reason is that the galaxy clusters are the most massive gravitationally bound objects in the universe, and they are key to further understanding it. But they are often assumed to be in hydrostatic equilibrium, although there are strong hints that part of the gas pressure is provided by bulk and turbulent motions, which are induced by accretion, major events, aging activity, etc. And so this transfers kinetic energy, which is injected on the large scale down to the small scale, where it's dissipated. And those contribute to the thermalization of the gas, and hence the virialization of the halo. But so to characterize those movements, we need velocity measurements, which can be obtained from the gas emission lines. And an example of how the turbulence impacts the line shape is shown here, where we see we have a broadening of the line, as well as a shift of the centric line. And the thing is that this requires high spectral and spatial resolution, to detect or to properly study those impacts, which is not available in the current observatories, but will be with the Athena X-IFU. So our goal here with this specific study is to assess the capabilities of the X-IFU to measure the turbulent and bulk motions in galaxy clusters, and find the optimum strategy of observation for such measurements. So in order to do that, we perform simulations using a 60 end-to-end simulator with as input a toy model representative of non-whole core galaxy clusters at a redshift of 0.1. And we run the simulation for several pointings and merge them together, as shown on the count image here to the right, which was a merging of 19 X-IFU pointings. And we take advantage of the X-IFU being an imaging spectrometer to create bin regions of multiple pixels and decrease the signal to noise ratio. And we can see on the right at the bottom here an output spectrum from one of those bins with clear emission lines, which we use to map the physical parameters of the cluster, such as the centroid shift. And so you can see such map here of the centroid shift, as well as others for the temperature and the emission measure. And so the this is key because we, as diagnostic, for turbulent and bulk motion, we rely on the structure function that's calculated from the emission line centroid shift, this is basically similar to a special correlation function. And so here I'm showing 3 examples of maps of this centroid shift for various geometries of observation that we could do, either 19 pointings altogether, or like just 9 as a cross, or only 5 in line. And so from those maps, we can extract the structure function that I mentioned before, which is what's shown at the bottom left. But what we can also do is actually for a given model, we can predict the structure function using the formalism from Claire and Al, which are shown on the right. And so, assuming that the turbulence parameters from our simulation are not known, we can try and recover them through MCMC fits using the structure function for prediction. So that would be a way to recover the parameters from the turbulence by doing this. But then what we can also do and want to do is to compare all the structure functions from the various strategy of observations, after, of course, accounting for complete error budget, which is ongoing now. And so the idea is to see how well we can recover those parameters depending on the geometry. And the goal is to optimize the observation time in the end. So those 2 different aspects of this simulation work are ongoing. And yeah, that's where we are at now on this. So just conclusion and some perspective on this work. So basically this PhD work contributes in different aspects of the X-IFU development, both like instrumentation and a bit of science. So yeah, the work is ongoing on both aspects. So I'll leave you now, I guess, with the bullet points here. And thank you for your attention. And if you have any questions, please ask.
Great, thank you very much, Sophie. Thank you for the talk, and very interesting indeed. If now I open the floor for a few questions, if people have, again, from either from the chat or from YouTube, you can raise your hand. While we are waiting, I take the chance to myself make a question. Actually, I have first a question related to the test detector. So you were, I'm not so the test development. So you were mentioning there is, I understand that, and when you put the simulating the aging, basically you see, if I understand correctly, basically a loss of 18 to 21%, more or less, if I understand. So I was wondering whether, just to give us a sense, is this acceptable or somehow, or is something that really needs to be improved?
So there is actually some work that's being done at the moment by the science team, in the like X-IFU consortium, to try and study the impact of this non-Gaussian component in the line, and how what we can actually accept. So right now there is a requirement for this, but which is still like TBD. So of course, so that's still to be defined, for sure. But the thing, is that we don't want this tail to be too strong, of course. So I guess how much, that's the science team will tell us. But there's also the problem that even if it's small within the requirements, what's important is that it needs to be characterized before we do all the gain calibrations and things like that. Because if you do all your calibration measurements, if your detectors have a given line shape, and then because you mishandle the detectors during the rest of its life until it's flown, while you install it in the satellite and all of that, and this increase this tail, for instance, that can lead to some problem, because then it means your calibration was not, really. So it's important, to try and
And to which rate, sorry, just a curiosity, to which rate is the aging effect affecting so you start from 0, basically loss, to 20%, let's say, in which age? Which time scale?
Yeah. So actually, you don't really start at 0 exactly, because you still have some components from electron escape, stuff like that.
Yeah, it's never 0.
Maybe 1 to 4%, let's say, and then it goes to 20. And the rate at which that happens is exactly what we are trying to determine now with those tests. So the first 2 steps that I did were those, like 50%, and then even higher. And we've noticed that after 2 weeks at 55% in average, we already start to see this tail at maybe 16%. So now I need to perform further, like smaller steps, in order to see exactly when they start happening, and define exactly how, like what you're asking, how fast this is happening, and so this is still ongoing research.
Okay, good. Thank you very much. So I see that Dietrich has a raised hand. So Dietrich, please go ahead with your question.
Yeah, thank you. Very interesting story about the test detectors. If the ELT had detectors with energy resolution, which is just a tenth of what you have for Athena, this could save the equivalent of tens of millions of euros. Very exciting story. Can you tell us a little bit about some of the detector characteristics and one or all of, say, linearity, the on-chip crosstalk, pixel-to-pixel crosstalk, and hysteresis due to overexposure?
Okay,
so linearity, crosstalk, signal remnants.
Okay, so on the linearity part, so of course, if you start for the highest energies, X-ray energies, you will have some non-linearity in your line shape. So I guess that exactly at which energy you would actually start having any issue with that, I have to say I don't have the number in mind right now. But yeah, this is of course something that happens as you go to higher energies like X-rays. You ask about the crosstalk. So that's also one of the things that other people in the team are looking at. So you can have indeed crosstalk either from the electronic itself, so electrical crosstalk, or from the detectors to another. And so there's also all sorts of like a test in order to characterize this, which are being done in the lab by other members of my team, actually. So yeah, that's also the sort of thing that are being looked at and studied. And you were asking
signal remnants after overexposure.
Yeah, okay.
Do the detectors show an afterglow after overexposure, or does it take some time to recover from such an overexposure?
So the time to recover, I mean, is fairly small, but the nice thing actually about the Athena is that it will have, on the mirror, have the numbers on my table. So basically sorry, I'm trying to find the slide again where I have this. Let me share my screen for a second. Okay, do you see the slide? Yeah. So we have this count rate capability, the up to 10 millicrab for the nominal energy resolution. So which is the 2.5 eV, not to 7 kV, like that I said. And then if you have even like stronger sources, Then, of course, to start, we have some degradation in the energy resolution, and we can go up to 1 crab with a 10 eV resolution and the beryllium filter in there. But so for sources up to 10 mini crab, the requirements on the energy resolution are still met. Yeah. I don't know if that's actually answer your question about the other.
Yeah, thank you very much for your answers.
Great. Thank you again, Dietrich, for the question. Thank you, Sophie. At this point, I think we can close the event by thanking again the speaker of today, Oliver and Sophie, for nice talks, and congratulations, and good luck with your future career, and looking forward to see you in real life, sooner or later. I'm sure it will happen soon. So to welcome you at ESO, hopefully. So thank you very much again. And with this, we close the event of today. And thanks also for the attendees, to people for coming and for making questions. And again, let me remind you that the talks are available online, so they can be seen offline anytime. There is a dedicated webpage YouTube channel on which these talks can be seen again. With this, I'll close the event. Thank you very much again, and see you next week. Bye-bye, everyone. That's all. Thank you.
Yeah, bye-bye. Thank you.